Hey guys, it's Miss Johnson here, and I'm here to bring you the second half of the 9-6 notes for today. These are our last notes for the whole trimester. We picked up, or we left off in the video on number 3, so I'm going to pick up with number 4 here and get us through the last 4 examples on the back page, and then you'll be off and going on your own. So in number 4, we're looking at exponential growth. It says the population of a city of 1 million is increasing at a rate of 3% per year. If the population continues to grow at this rate, in how many years will the population have doubled? So in how many years? That tells you that T is our question. T is what we're trying to find. So then let's see if we can identify everything else that we know. We know that the starting population is 1 million. That's A. We know that the increase rate or the growth rate is 3%, so R is 0.03. And we know that we want our population to double. So that means if the population doubles from 1 million, our new value will be 2 million. So let's set this all up. That means I have 2 million is equal to the 1 million times the 100% plus the growth rate 0.03 raised to the t power. Now I know that I need to get rid of everything in that power or outside of that power first, so I'm going to divide by a million. Divide by 1 million. And obviously 2 million divided by 1 million is going to be 2. And that's where that doubling comes into play as well. So I have 1.03, I can just add those together, raised to the t power. And I know that I want to take the log of both sides to get that t out of the power position. So to get the t out of the power position, I'm going to do the log of 2. That moves my t out to the front, so I have t times the log of 1.03. And then to get the t alone, I need to divide by the log of 1.03. So in your calculators, that's what you would plug in. I would divide the log of 2 divided by the log of 1.03, and I get about 23.4495, and that keeps going, is approximately my t. So if I was going to round that, I could maybe say about 23.5 years. So let's take a look at number 5. It says home values in Millisport increase about 4% per year. Mr. Thomas purchased his home 8 years ago for $122,000. What is the value of his home now? So I know that it's an increase. That means I know I'm looking at exponential growth. So I know I want the equation y is equal to whatever my starting amount is times 1 plus the growth rate to the t power. And then let's identify everything that we know. I know that this has to be my A, that's my starting amount. I know that 4% is my R, so R is 0.04. And I'm asked for 8 years ago, so that's got to be my T. So then let's plug it in. I have Y is equal to 122,000 times 1 plus 0.04. Don't forget to make that rate a decimal, raised to the 8th power. So 122,000 times 1.04 raised to the 8th power is going to end up giving me $166,965. And you can plug that into your calculator to just verify. But I'm looking at option C here. That's my best choice. All right, let's take a look at a couple of other models that we can use. Here's another model that's given to us by exponential decay. This one has that E that we talked about in section 9.5 as a base here. Exponential decay, that's when it's decaying continuously. We talked about that word continuously, and when something's changing at a continuous rate, that means I need to use a base of e. So for exponential decay, I have y is equal to a times e to the negative kt power, where k is some sort of constant. T is still going to be my time, a is still going to be the starting rate, or the starting amount. And then exponential growth, I could have a times e to the positive kt power. So negative k is going to decay, positive k is going to grow. So let's look at number 6. It says the half-life of a radioactive substance is the time it takes for half the atoms of the substance to disintegrate. All life on Earth has carbon-14, which decays continuously at a fixed rate. The half-life of carbon-14 is 5,760 years. That is, every 5,760 years, half of the mass of carbon decays away. What is the value of the constant K in the equation for carbon-14? So let's think of what we know. We know that we're talking about the half-life, or we know the half-life, and the half-life means that I'm going to have 0.5 of whatever's left. So that's like my ending amount because I'm talking about when it starts from 100% and goes down to 50% or 0.5. So I know that my starting amount is going to be 1 because I'm starting with 100% of it. And then the time, I know that this is the time because that is my half-life. So let's plug all that in. I have 0.5 equals 1 as my starting amount times e to the negative k times 5,760 years. And I'm trying to find that k. So first of all, I can get rid of the 1 because dividing by 1 is not going to do anything. So I have 0.5 is equal to e to the negative k times 5,760 years. Then the next thing I notice, since this is a base of e and I need to get that power out of its exponent position, I'm going to take the natural log. So the ln of 0.5 is equal to negative k times 5,760 times the natural log of e. And we learned back in 9.4 and 5 that the natural log of e is in fact 1. So I don't need it. So I have the natural log of 0.5 is negative k times 5,760. Now I need to get rid of both the negative and the 5,760. So I'm going to divide by both of them at the same time. Negative 5,760 divide by negative 5,760. So this is what you can plug into your calculator. The natural log of 0.5 divided by negative 5,760, you should end up with about 0.00012. That's going to give you your K. So that's that constant that we found, which gives us the half-life of carbon-14. So now let's take a look at number 7. So in number 7, I now am asked for a certain strain of bacteria, K is 0.872, when T is measured in days, using the formula Y equals A times E to the KT power, because now this bacteria is growing. How long will it take for 9 bacteria to increase to 738 bacteria? So here's what we know. We know that this is my starting amount. I know that this is my K. Um, this is what I'm trying to find because it's asking me how long. And I know that this is going to be my ending amount. So let's plug all that in. I have 738 is equal to 9 times e to the 0.872 t power. And then I want to solve for that t. So first thing I need to do is divide by the 9, get rid of that 9 that's on that right-hand side. 738 divided by 9 gives me 82. So I have 82 is equal to e to that power, 0.872 times t. And then I'm going to take the natural log of both sides because, again, I'm using a base of e. So I have the natural log of 82 is equal to 0.872t times the natural log of e. And again, we know that the natural log of e is 1, so I can get rid of it. And then I just take this and divide by the 0.872. Divide by the 0.872. So I have the natural log of 82 divided by 0.872, and I get 5.05 is approximately t. If I were to label this, I could say that this is about 5 days. I'm measuring time in days here. All right, so that is the end of our notes for 9.6. One thing that I want to make sure you're aware of, this constant K that we found in number 6, you're going to need for your homework. I believe it's number 5 on your homework. You're going to need that constant K that we found. So Just keep that in mind. You can go ahead and work on your worksheet, and if you finish that, you can work on the Chapter 9 review packet. Have a great day, and I will see you tomorrow.